We can think of matrices as encoding linear transformations. Now we've seen how a matrix transforms vectors to other vectors, but we can also consider transformations of objects whose index is downstairs, for instance. These are called differential forms, one forms, or just forms for short. They are also called dual vectors. From a matrix perspective, dual vectors are some kind of horizontal matrix of elements. They naturally fit together with vectors to produce scalars. So if you put the upstairs index of a vector together with the downstairs index of a dual vector, you get something with no free index, and so you get a zero tensor, which can also be called a scalar. If we want scalars to be truly scalars under transformations, then if we transform a vector with a matrix M, we have to transform the one form with an M inverse so that the scalar remains invariant. We can do out this calculation by simply replacing Vi and omega I with their corresponding transformed versions involving the matrix and the matrix inverse components. We end up finding the inverse matrix's downstairs index contracted with the upstairs index of the transformation matrix M. This is the component version of matrix multiplication. The repeated index shows how the kth row of M inverse dots together with the jth column of M. Now, M inverse times M as a matrix equation should give you the identity matrix. So we need to write the identity matrix components, and these get a special name. They're called the Kronecker delta tensor. This has the property that when the two indices are the same, you get the value 1, and when the two indices are different, you get the value 0. If we replace M inverse times M in our component equation, notice that there are free indices k and j, so the delta matrix, the delta components, that show up are delta kj. There's now a double summation over the index k and the index j, but remember that the delta symbol will be 0 unless k equals j, so the double summation collapses to a single sum where k equals j. This means that we end up with the product omega j vj with the summation over j, and this is equivalent to vi omega I, which is where we started. Part of the power of index notation is that the index positions reveal the transformation properties of the particular tensor type object. So if you have an upstairs index, you get a factor of the regular matrix components mij. If you have a downstairs index, you get the inverse components, M inverse ij. It's kind of clunky to keep writing M inverse, so we define a convention where the reversed order of the indices, so we have M downstairs j, M upstairs I, is equal to M inverse upstairs I, and then downstairs j. Given these rules, you immediately know how a tensor transforms just by looking at its index structure. So to take an example, let's say we have tensor T with an upstairs I and then a downstairs j and a downstairs k. The transformation will involve regular matrix components of M for the upstairs I index, and then an inverse matrix components of M for the j and the k indexes. We now have one way to answer the question, what is a tensor? A tensor is a collection of components that all transform in particular ways under matrix or linear transformations. The index structure that tells us how to fit these components together is determined by the tensor's transformation properties. There is ultimately a very deep story related to all of this, connected to group theory and the theory of linear transformations and their representations. But this will be enough for us for now.